Good evening one and all. Today is 9th June 2023. We are going to start the module 5. This is lecture number 28. We are going to start module 5, which is titled Hybrid Drivetrain Design. In the module 4, second part, we have seen the basics of hybrid drivetrain design. We have seen series hybrid and parallel hybrid and their configuration, advantage, disadvantage, limitation, etc. In this module 5, we are going to see both this drivetrain in detail. This is the first part of module 5, which we are going to start today. It is called a series hybrid electric drivetrain design. Under this, we are going to first see the operation pattern of series hybrid electric drivetrain, which is also called as a electrically coupled drivetrain. We are going to see the control strategies. Under this, there is PPS control, thermostat control. PPS control is little complex looking graph or characteristic, but it is not difficult. Thermostat control is comparatively easy. And at the last part of this module 1, we are going to see sizing of major components of this series hybrid electric drivetrain. Under the major components, first there will be the design of traction motors, how to design the power rating, how to design or how to set the specifications of traction motors. Next, we are going to see the power rating design of engines, because whenever I am saying it is series hybrid, it will be comprising the battery as well as the primary power source, that is engine. So design of both, that is power source, engine and traction motor. All the design considerations we are going to see here. There is a new concept we are going to see here. The concept is not new, but name will be new, used here for the first time, which is called as peaking power source, or we are going to mention it as a PPS. All this we are going to see in the first part of module 5, and we are going to start with the operation pattern of series hybrid electric drivetrain today. In the second part of this first part, that is series hybrid electric drivetrain, we are going to see in our textbook EHV module 8, page number 229. Next, we are going to see parallel hybrid electric drivetrain design. There also we are going to see mainly two types of control strategies. One is engine on-off control, one is state of charge control. And under the design considerations, we are going to see the design consideration for engine, motor and peaking power source. So we are going to see or start with series hybrid electric drivetrain today. We are mainly going to see two things. First one is the operating patterns, second one are the different control strategies for series hybrid electric drivetrain. So it will be taken from the book of EHV module 8, page number 229. Design principle of series hybrid electric drivetrain. So whenever I am saying series hybrid electric drivetrain, first thing that comes to our mind is how is it different from EV? Because basic difference between electric vehicle and hybrid electric vehicle, what are they? So the series hybrid electric drivetrain actually was derived from EV, that is electric vehicles. EVs are having some positive points. The positive points are zero mobile pollutant emission, multi-energy sources and high efficiency, but it is having some 2-3 disadvantages or limitations. So the prime limitation of electrical vehicle technology is limited driving range. So once the battery is fully charged, at that time how long the vehicle will go in one charging, that is actually comparatively less compared to the IC engine based vehicle. Second is limited payload and volume capacity. That means the battery itself is very heavy and bulky. That actually eats up lot of payload in case of electric vehicle. That means its person carrying capacity or load carrying capacity reduces, because from the beginning itself it becomes very heavy. Third main disadvantage of electrical battery based vehicle is long battery charging time. But then also EVs are preferred over IC engine based vehicle because of their zero mobile pollutant emission, and efficiency of the electric vehicle are also quite high. In the developed countries or in countries like India also, where the cities are getting heavily polluted because of IC engine based vehicle, everybody has started thinking very seriously about only EV based vehicles. So the initial objective of developing the hybrid electric vehicle, or basically series hybrid electric vehicle, was aimed at extending the driving range by adding an engine or alternator generator system to charge the batteries on board. That means the vehicle will not be completely electrically driven, but it will be driven by some engine, some alternator, that is a generator, which will be charging the batteries on board, and the batteries will be driving the vehicle. Okay, so we have seen actually the basics of series hybrid in the previous module. We have seen there are 8 to 9 modes of operation. So one mode was the source 1, which is engine, it is driving the vehicle. Second was the secondary power source, which is the batteries, that is driving the vehicle. Third is when there is huge amount of power requirement, at the time engine and battery together, they are driving the vehicle. One another mode was there, which was 8th or 9th. At that time we had seen that the primary energy source, that is engine, it was charging the secondary energy source battery, and it was not giving any power to the output transmission. So primary source was charging the secondary source, and secondary source, that is battery, is actually driving the whole vehicle. So in that case, amount of pollution or amount of emission of pollutant in the air, it becomes actually very less. So the initial objective of developing series hybrid electric vehicle was aimed at extending the drive range by adding the engine alternator system to charge the batteries on board. So even if the battery get discharged while driving the vehicle, for some time we can stop the vehicle, we can start the primary energy source, that is the engine generator based energy source, that will charge the battery, and battery will drive the vehicle again. So we will generally not fall short of driving energy at any time in case of series HEV. Features of series HEV. So vehicle performance in terms of acceleration, gradability, maximum speed is completely determined by the size and characteristic of the traction motor drive. So designing of electrical motor in case of series hybrid electric drivetrain is a very important part of it. And we know what is meant by drivetrain. In case of series hybrid, there are two powertrains. First one is driven by engine generator, second one is driven by the battery, and together whenever we are adding these two powertrains, we are getting the hybrid electric drivetrain. So the vehicle performance of this series hybrid electric drivetrain is mainly driven by the traction motor drive. For EVs, the motor power, capability and transmission designs are one and same. However, drivetrain control is essentially different from the pure electric drivetrain due to involvement of additional engine generator unit. So in case of only electrical drivetrain, we have found that only the charging from the external plug or regeneration of energy from the output to the input, these were the two main sources of electrical energy in case of EV. But in case of series hybrid electric drivetrain, there are mainly three sources by which the battery gets charged. First one is from the primary source to the battery. Second one is the battery gets charged directly from the plug, and third one is regenerative braking. So that's why it is said that the drivetrain control is essentially different from the pure electric drivetrain, that is EV, due to involvement of additional engine or generator unit in case of HEV. Discussion here will focus on the design principles of engine alternator system, the drivetrain control, and the energy and the power capacity of the battery pack. So whenever I am saying principles of engine alternator system, that means design of PPS, second one is drivetrain control, and third one is the battery pack design. So motor design, battery design, engine design, and their specification are the three main topics in case of any hybrid electric drivetrain. So the peaking power source is a new term actually we are finding here. It will replace the battery pack. So we are not going to talk about battery pack because the battery pack will renamed as peaking power source. So what is meant by peaking power source? Peaking power source is generally not in use while the vehicle is being driven. Battery is not in use when the vehicle is driven mainly. At that time, mainly the engine generator power will drive the vehicle in case of series hybrid. So the primary source, that is the engine generator set, that will mainly drive the vehicle in the normal operation. But whenever huge amount of power is required, whenever there is a bumper power required, at that time this peaking power source or battery, it will chip in. So for the normal operation, for the constant operation, engine generator arrangement will drive the vehicle, and during peaking power requirement or huge power requirement, sudden huge energy requirement, at that time this PPS or battery will come into use. So HEVs have major function of the batteries is to supply the peaking power. This is why there are two sources instead of one. In case of EV there is only one source, that is the battery. In case of HEV there are mainly two sources. One is for constant driving, another is for peak power requirement based driving. So they can be replaced, that means the battery can be replaced with other kind of sources like ultra capacitor, flywheel and combinations. So primary source will be always so actually there are two types of primary source. One can be the evergreen generator and IC engine kind of a thing, and this whole thing can be replaced by fuel cell also. So the primary source can be engine generator or fuel cell. Secondary source can be battery, ultra capacitor, flywheels, etc. So these are the combinations we have to remember. This diagram we have seen actually in previous module, that is whenever I am saying a vehicle is requiring too much of dynamic kind of a power, this whole dynamic load power can be divided into two categories. First one is average power, which is supplied by a high specific energy source, which is nothing but the engine generator, and the second power requirement, which is a highly dynamic power. This thing is being supplied from the battery, or which is called as a PPS, or which is called as a peaking power source. So in designing the control strategy of hybrid vehicle, one powertrain that favors the steady state operation. So this top you are finding, this is the average power. Engine is actually driving or producing this steady state operation power requirement, such as engine fuel cell may be used to supply this average power. So the load power is composed of two components. So at the top here is given these are load power requirements. One is a steady power. So this whole thing is divided into two parts. So this is the overall requirement. It is having average power as well as bumper power requirement. So this is the constant value, and below is the dynamic power requirement, which is a zero average. So for the first case, it is said that the engine or fuel cell can be used as a source for the primary power or average power, and another powertrain, that is electric motor or battery based electric motor, may be used to supply the dynamic power. So whenever there is a big fluctuation, that part can be supplied by a specifically designed battery. Total output energy from the dynamic powertrain will be zero in an effective entire driving cycle. This implies that the energy source of the dynamic powertrain does not lose its energy capacity at the end of driving cycle. It functions only as a power damper. That means whenever too much power is requirement, whenever some extra bumper power is required, then only then this battery and motor combination is going to act. In remaining other time, it is going to be silent, it is not going to supply any power. At that time, the energy will be taken from the primary source, which is nothing but engine and generator. So decomposition of load power into steady state dynamic components, the previous graphs actually. That graph is saying three things. Number one, in a hybrid vehicle, steady power may be provided by IC engine or fuel cell or a Stirling engine. Second thing, the IC engine or the fuel cell can be much smaller than that in a single powertrain design, because dynamic power is taken from a dynamic power source, which is nothing but a battery motor, and then engine can operate steadily in its more efficient region. So if it is a purely IC engine based vehicle, or if it's a purely fuel cell based vehicle, that means only single source, in that case IC engine and fuel cell will be very big in size, because in that case the IC engine or fuel cell, it has to supply the constant average power as well as it has to supply the bumper power. But whenever we are designing a HEV, that is hybrid electric vehicle, there size of IC engine and size of fuel cell will reduce, because in that case they have to supply power only in constant power requirement. Dynamic power will be taken from the dynamic power source, which is nothing but a battery or flywheel or ultra capacitor and all. So actually the main load get distributed among the primary source engine and secondary source battery based motor driver. Dynamic power may be provided by an electric motor powered by batteries. So they are specifically or especially designed batteries, they are not normal batteries. These batteries are having actually high power capacity. Okay, so the dynamic power sources can be electric motor, which are powered by batteries, ultra capacitor, flywheels and their combinations. This is the diagram of typical series hybrid electric drivetrain operation. You have seen a detailed diagram in the module 4 also. There is little more elaboration given in this series hybrid electric drivetrain operation, which I am showing in module 5. In this case, you are finding this is a electric vehicle. So what are the inputs to any kind of drivetrain? So the inputs can be 3 inputs. That means whatever inputs are coming from driver, actually there are 3. Number 1, that is the acceleration, which is the main input which the driver is asking from the vehicle. Number 2, that is a brake, because whenever there is traffic in front, or whenever somebody comes, or it's a city kind of driving, at that time brake is a very important thing. So this brake in case of hybrid electric drivetrain will be a hybrid brake. Hybrid brake means it will be a combination of electrical braking and mechanical braking. And as we have seen, mechanical braking is mainly a lossy thing. Whenever there is mechanical braking, it's only power loss. But electrical braking is actually regenerative braking. It's a power gain, because whatever power we are saving during electrical braking, that actually comes back to the secondary power source, that is battery, and it actually charges the battery. So here we are finding there are these 2 inputs, that is brake and acceleration, and there is a third input which is called as a direction. So brake and accelerator control is there in the legs, and direction control is there in the hand, which is nothing but through the steering. So all those 3 inputs are constantly changing the course of action of a vehicle. So that 3 things together, it is called as the operation commands. So operation command means 3 things, that is accelerator, brake and direction. So these 3 are coming to the vehicle controller. This is the main microcontroller, or the main part of the ECU, and this controller actually is connected with all the sub controllers you are finding. So vehicle controller is connected to mechanical brake controller. So this is another slave kind of microcontroller. You are finding that this is connected to the wheel 1, this is connected to the wheel 2. So all this brake related sensing, anti-lock braking system and other thing, they are actually connected here. They are connected to mechanical braking, and they are taking the brake related signal to the vehicle controller. Vehicle controller should come to know everything, all the parameters of the vehicle. So this is vehicle controller, and this is the braking mechanism control. Next you are finding that vehicle controller is connected to the engine controller also. So engine controller, engine is the main energy source. So this engine actually is connected to the fuel tank. So here you can show a very small fuel tank which is connected to the engine, and engine output, which is mechanical, it is given to the generator. Generator is taking the mechanical rotation input, and it is producing DC or AC electrical output depending on the type of motor. So if this motor is DC, generator will be producing DC, or if generator is producing AC, then this coupling device will be having a rectifier in it. So it is taking the AC from the generator, it is converting it into DC, then it is giving the DC power to the motor controller and to the motor. So depending on the size and type of this motor, this coupling device or electrical coupling device has to act accordingly. So this is not only coupling the power from the PPS source. So this is a peaking power source. Peaking power source is nothing but the battery, and this peaking power source can be charged directly from the plug-in, and this peaking power source, any state, how much is the state of charge, how much is the state of current or voltage and all those things. So all the details of this secondary source or peaking power source is continuously being fed to the vehicle controller, and accordingly the engine controller will take decision that how much power should be taken from the engine, how much power should be taken from the peaking power source to satisfy the overall power requirement by the vehicle. So that's why you are finding all these things are in a closed loop. So vehicle controller to engine parameters are sensed, it is taken back. You are finding here, this is called as the engine speed and the throttle position control. So throttle is nothing but the opening or closing of the fuel of the engine. Okay, so more power is expected from the engine. At that time the engine controller will open the throttle accordingly, and engine will be getting more fuel, and engine will generate more power. Okay, so this whole thing is in a closed loop. Engine operation, it is being closely tracked, closely controlled, and this engine controller has to report everything to the vehicle controller. So vehicle controller is the, you can say it is the principal of the whole system, and engine control is like a HOD, right? And engine, generator, all these things are, you can say, teachers. So vehicle controller principal is having control over HOD, HOD is having control over teachers. This is the hierarchy. Same thing we are finding, this peaking power source, all the inputs are sensed. So we have seen battery management system in the module number 3. There also all this are sensed. So this peaking power source, state of charge, state of power, voltage, current, everything is being continuously fed to the vehicle control. So this is a closed loop, and this is a tracking system for both the power sources in case of series hybrid. So this generator is giving electricity to this coupling device. Peaking power source is also giving electricity to the coupling device. The whole electric power is getting combined here. They are getting converted to DC or AC depending on the type of the motor. So more than 2 kilowatt hour, we are not going to use DC motor. Less than 2 kilowatt hour, we are going to use DC motor for driving of the vehicle. So for very smaller vehicles, electric vehicle, we can use DC series motor. For bigger vehicles, we are going to use BLDC motor or switched reluctance motor, that is called as a SRM. So motor controller, again you are finding that this motor controller is also being controlled by the vehicle controller, and motor controller parameters or motor parameters are also continuously being fed to the vehicle controller. That path is not shown, but it is here. So you are finding here mainly 3 types of power transmission, or 3 types of signal is being transmitted. One is a mechanical connection. Here you are finding that from motor to the transmission to the wheels, these are all mechanical power transmission. And here this is wheel speed is being sensed. So this axle speed is the output speed. This axle speed is being sensed continuously, and it is being given to the vehicle controller. So depending on this axle speed, or depending on this vehicle speed, this vehicle controller is going to take decision that how much more power has to be input to the engine, generator or PPS, so that the output velocity for the vehicle will be increased or decreased. So there are many sensors. You are finding there are brake sensors, there is brake fluid sensor, and caliper sensor, and all those things. Anti-lock braking system, it requires sensor. There is continuous measurement of velocity of the vehicle, that thing is there. Steering, there will be sensor. Engine, generator, SOC, and electrical coupling motor, everywhere too many sensors are fit. So there is a very high-end device, and it is totally wired, and it is totally controlled by 70-80 different microcontrollers. So this whole process has to be explained. If typical series hybrid electric drivetrain operation is being asked, you have to explain this part. And a vehicle with series hybrid electric drivetrain is propelled by a traction motor. So here you are finding these are the electrical power. So whatever power goes from the peaking power source to electrical coupling, generator to electric coupling, all electrical power. From electrical coupling to the motor controller, there is also electrical power. Motor controller to motor, electrical power. So all the signals are given by a single line. Okay, and there are signals. Signals means whenever there is some sensed thing. So from motor controller to vehicle controller, all the motor parameters are being taken. All the signals are being conducted from the vehicle controller to the motor controller by means of signal. So there is small electronic signal. Peaking power source, all the energy, all the state of charge, current, voltage, all these signals are taken to the PPS. The engine speed or vehicle speed is continuously being fed back to the vehicle controller by means of signals. So you are finding there is a second type and third type of signals. So the powers of both power sources are merged together in a power electronics based controllable electrical coupling device. So this is a very important thing. This is the coupling device. Many operational nodes are available to choose from according to the power demands of the driver and the operational status of the drivetrain system. So depending on the operation commands that is coming from the operator. So operator is nothing but driver. Vehicle controller will decide how much power is to be extracted from the primary source, secondary source, and it has to be combined in which proportion in the electrical coupling device, and then how the motor is to be driven. So for any situation, different 9 situations where different 9 modes were explained in the module number 4. As per that, the vehicle controller will decide and give the power accordingly to the transmission system. So if asked in this module, so module number 5, if they are asking explain typical series hybrid electric drivetrain operation, in that case this diagram is to be drawn, and each block you have to explain in your own language. So series hybrid electric drivetrain operating system, same thing is continued. It is saying that the engine generator system is mechanically decoupled from the drive wheels as shown in the above figure. So what is the mechanical device? Mechanical device is engine, but this engine is connected with the motor or transmission, there is no electrical coupling. Sorry, there is no mechanical coupling. I'm sorry, it is electric coupled but mechanically decoupled. So you are finding here engine is producing mechanical output and that's it. After that, there is no mechanical things. Directly at the output of the motor, there is a mechanical signal generated or mechanical power generated, and it is given to the transmission. So very important line given here, the engine generator system is mechanically decoupled. So this engine generator system, it is electrically coupled, but this is mechanically decoupled from the transmission system. Speed and torque of the engine are independent of the vehicle speed and traction torque demand, as they can be controlled at any point of operation by the speed torque plane. So you are finding that depending on the command, operation command, the vehicle controller can increase or decrease the speed and torque of the vehicle just by controlling the output motor. And this motor is actually getting the input from engine generator set as well as from the peaking power source. Whenever the vehicle is going down, that means the vehicle is going downward, at that time there will be a regenerative braking. At that time this wheel will rotate and the energy will go from, so this motor will act as a generator in that case, and the power will be fed back from the motor to the motor controller to the coupling device to the peaking power source. That means this battery or peaking power source will get charged when there will be electrical braking or when there will be regenerative braking. So all these things you have to explain. And this is a very important thing which is called as a engine characteristics of optimal operating region. Same thing we have seen previously in case of EV, also in case of IC engine based vehicle also. So this is kind of a 3D contour graph which is shown in 2D. You are finding that this region, that means around, so x-axis is crankshaft RPM, or you can say engine rotation speed. So x-axis is RPM, y-axis is what is the power generated in the engine. You are finding that when the crankshaft RPM is around 4500 to 5000 here, maximum power is produced. This power is around 70 kilowatt you are finding, or 68 to 70 kilowatt. But whenever the power is maximum, efficiency is not maximum. Okay, so that means in this case the loss also will be very high. Where is the efficiency maximum? So you are finding this is the peak of the efficiency track. So in this point, that means starting from around 1500 up to around 3000. That means around you can say around 40. So if you consider this 5500 as 200 RPM, okay, so half of it, so around you can say 70, 80 to 100, 102, 120 kilometer speed. That means this 500 to 5500, whatever is the engine crankshaft RPM, this you have to recalibrate in terms of 0 to 200 kilometer speed, because this crankshaft RPM is only getting converted to vehicle speed. Okay, so this is crankshaft speed. I'm just asking you to replace these values in between 0 to 200. So in that case you will be finding starting from you can say 30% of 5500, that means around 60, 70 up to around you are finding 100, 120 kilometer per hour. So around 60 up to 120 kilometers. So this range you are finding that this is called as optimal operating region. Optimal operating region means this will be the highest efficiency. That means in this region, if you are driving the vehicle, that means if you are driving the vehicle in between 60 to 100, 120 kilometer per hour, you are going to achieve maximum fuel efficiency, or efficiency of the whole drivetrain will be maximum. So maximum output power is different thing, maximum efficiency is a different thing. This is called as a specific fuel consumption, gallon per kilowatt hour efficiency. So in these directions, this fuel consumption is more, energy is more, but fuel consumption is also more. But here, whenever you are driving this vehicle in this region from 60 to 120 kilometer per hour, you will be finding that in comparatively less fuel consumption, the vehicle is generating high output power. So generally the engine should be controlled in such a way that it always operates in its optimal region. Optimal region always gives us best efficiency, or lowest usage of fuel and highest amount of power. That is called as optimal region. So where fuel consumption and emissions of engines are minimized. Very important thing, whenever the vehicle is acting in optimal region, at that time the pollutant generated by the vehicle is also minimum, because HEV is not EV. HEV means this is hybrid electrical vehicle. This is actually run by a combination of engine which is driven by gasoline, fossil fuel based thing, and EV. So whenever I am saying it is HEV, This also pollutes the nature because it is using fossil fuel based vehicle. But if you are driving the vehicle in this range, efficiency range, that is 60 to 120, in that case the efficiency will be optimum, that is one thing, and pollution will be as less as possible. So due to the mechanical decoupling of the engine from the drive wheels, this optimal engine operation is realizable. However, it heavily depends on the operating modes and the control strategy of the drivetrain. So there are 9 different control strategies. Which control strategy will give us this optimal region or maximum efficiency? This has to be decided, or this has to be designed, and it should be known to the driver very perfectly. So last 3 slides are there. In this slide we are going to see series hybrid electric drivetrain, what are the operating modes. So we have seen previously in previous module there are some 9 operating modes. In that, how many of them are taken into series hybrid electric drivetrain, that we are going to see. So the drivetrain has several operating modes that can be used selectively according to the driving condition and wishes of the driver. So these operating modes are as follows. So if the driver is going through highway, if the driver is going through a hill, if driver wants to go and drive through some jungle, so which out of this operating modes will the driver like to use, that the driver has to decide. So many modes will be there. Sometime the primary source will be operating, sometime the secondary source will be operating, sometime two sources will be operating together. So primary source is nothing but the engine generator stage, which is given by E/G. Secondary thing is called as not battery, but it's called as a PPS. So the different combinations of engine generator and the PPS that actually are deciding different operating modes for series hybrid electric drivetrain. So it is totally depending on the driver and driving condition and the wishes of the driver. We are going to see what are the different operating modes. So first one is hybrid traction mode. When driver steps hard on the gas pedal, large amount of power is demanded. So there is a sensor connected to the gas pedal. That sensor is connected to the vehicle controller main ECU. So if the driver is asking for too much of traction power or too much of power from the drivetrain, at that time both primary and secondary drivetrain will be working together. So driver steps hard on the gas pedal, large amount of power is demanded. Here both the engine generator and the peaking power source. Engine generator is the primary power source, peaking power source, this battery is the secondary power source. Together they supply the required power to the electric motor drive. You are finding that P demanded, so this is a demand from the driver. It is being satisfied by the engine generator power, that is PE/G and PPPS. Peaking power source and engine generator together, they are satisfying the demanded power or high demanded power by the driver. Here the engine should be controlled to operate in its optimal region for high efficiency and low emission, as shown in the figure before. So we have shown it in the figure of that bumper power and average power thing. So engine is there, that is PEG. Engine is there, it is mainly supplying the average power continuously. The PPS supplies the additional or bumper power to meet the traction power demand. This operation mode is expressed as this equation, which is already shown to you. So this is the first mode or hybrid traction mode. Second mode is peak power source alone traction mode. So you can see that P demand is equal to PPS. That means the secondary power source or peaking power source or battery, it himself is the only source or giving the power to the transmission. Third one is only the primary power source. That means only the engine generator is supplying the power. So P demand is equal to PE/G. So here the engine generator alone supplies its power to the meet the power demand. So this 2 and 3, they are not very heavily demanding cases, but yes, 1 is very heavy power demanding cases. So in case of 1, both the sources, the primary and secondary, has to work together. Regenerative braking mode. So whenever the vehicle is passing through the city or in a place where too much of stop go kind of thing, or too much of use of brake is there, in that case regenerative braking action is happening, or vehicle is going downward. In that case you are finding regenerative braking power is being produced. So when a vehicle brakes, this brake is mostly electrical brake, traction motor can be used as a generator, converting part of the kinetic energy of the vehicle mass into electrical energy to charge the peaking power source or battery pack. So last one is peaking power source charge from engine generator. So in this case actually whatever is the demanded power, that is being supplied by the engine, and engine is giving some power to the peaking power source as well. So in this fifth module, which is typical, you can say, hybrid electric drivetrain operating mode, okay, which was not possible in case of EV, that is peaking power source charging from the engine generator. That means suppose if demanded power is 100 unit, this engine generator will produce 120 unit. 100 unit will be given to the demanded power, and PPPS will be 20 units. So whatever is the total power produced by engine generator, some will go to the P demand, that is for the vehicle driving, and some will be given to the peaking power source. So you can say that this PPPS will be negative in that case. Though it is shown PEG plus PPPS, it should actually be PEG is equal to P demand plus PPPS, or in this equation if you are saying this PPPS will be negative. So when the energy in the PPS decreases to some bottom threshold, PPS must be charged. In this case, this can be done by regenerative braking or by the engine generator. So engine generator, we can take the vehicle inside, we can stop the vehicle, and we can run the primary source to charge the secondary source. This is one thing. In that case, P demand will be 0. So if you are stopping the vehicle and charging the PPPS, at the time PEG will be equal to PPPS. But second case, while we are driving the vehicle, then P demand is required, because for transmission some power is required. So engine will be giving power for vehicle driving, as well as engine will be giving the power to charge the PPS. So this we have seen in some mode number 6 or 7. In case of module 4, this also we have seen. So this P demand is equal to PEG plus PPPS. In this case, only difference is this PPPS is negative here, or actually somebody is writing PEG is equal to P demand plus PPPS. That also will be correct. Usually the engine generator charging is needed, since regenerative braking charging is insufficient in case this. So engine generator power is divided into two parts. One part is PEG, it propels the vehicle, and PPPS charges the battery. So you can say total power demand, or it can be said in other way, that is whatever is the total power demand, that will be PEG. So PEG is nothing but how much is power required from the for the propelling action, and second is PPPS is how much is the power required for charging the secondary power source. So this equation they are explaining here the way it is done. P demand is total power produced by the drivetrain. Among that, PEG is nothing but the power required for transmission or wheel driving. PPPS is nothing but the power to charge the vehicle. So PPPS is the charging the battery, P engine the propulsion of the vehicle. It should be noted that operation mode is only effective when the power of the engine generator is greater than the load power demand. So it should be noted that the operation mode is only effective when the power by the engine generator is greater than the load power demand. That means that is the same thing. If the engine can produce, engine generator can produce 120 units of power, 100 unit goes for the driving of the vehicle, 20 units goes for charging the battery. Very important thing. So three points are mentioned here at the top. So this is important thing you have to remember, and this may be asked in the question. So as shown in hybrid electric drivetrain figure, vehicle controller governs the operation of each component according to the number 1 traction power or torque command from the driver. So I told you there are mainly 3 command input coming from the driver. Which are they? Traction power command from the driver, feedback from each of the components, that means from brake, from vehicle speed, from the motor operation, from the peaking power source, state of charge, state of current, all those things. So there are many signal inputs are coming from the different components of the vehicle. What is the status of all those signals? So that also is a determining factor for how much power the engine generator and the peaking power source should produce. Third thing, also the drivetrain of the preset control strategy. So there are 2 control strategies I told you. One is PPS control and is thermostat control. So in each control, the strategy is different. So these are the 3 things. So as shown in the series hybrid electric drivetrain, vehicle controller governs the operation of each component according to number 1 traction power demand, number 2 feedback from each of the components, that is different sensor inputs, third one is drivetrain and the preset control strategy. So these 3 are the things which is deciding the series hybrid electric drivetrain performance. The control strategy objectives are, so what are the control objectives? Number 1, meet the power demand of the driver. Whatever is the power demand of the driver, that has to be met by the primary source and secondary source together if need be. Another control objective is operate each component with optimal efficiency. So if we are driving the engine, generator as well as the battery with optimal efficiency, in that case actually we are increasing the lifetime of both these things. So do not stretch the sources to the extent. Always try to work in the mid operating range. That will actually increase the efficiency and will increase the lifetime of the battery. We are going to get least pollution. All the positive points will be we will be able to achieve. So operate always each component with optimal efficiency. Third one is recapture braking energy as much as possible. So whenever the vehicle is going downward, it is in a downward slope, or whenever the vehicle is braking, use electrical braking more in case of mechanical braking, and try to recapture the braking energy as much as possible. This will actually increase the overall efficiency of the drivetrain. And number fourth is maintain the state of the charge of the PPS in a preset window. So always try to keep the battery fully charged. So PPS is nothing but the battery. So these are the four demands, or these are the four control objectives. So first three things, which are the controlling parameter of the engine as well as the battery, and last four are what are the control objectives for each of this drivetrain or overall drivetrain of series hybrid electric type. Last slide about this actually the introduction of the control strategies. So it is saying that the control strategy is a control rule that is preset in the vehicle controller and govern the operation of each component. So each component means mainly two energy generating components, that is engine, generator and battery. Vehicle controller receives the operation commands from the driver. So driver actually asking for power, he is not controlling. Controlling is actually done in the inside level by the vehicle controller. So that is the ECU who is asking the engine as well as the battery to act in a certain way so that the driver's demand is fulfilled. So the vehicle controller receives operation demands from the driver, that is vehicle controller is nothing but an embedded system, or microcontroller. It receives the operation command from the driver and feedback from the drivetrain from all the components, and it makes the decision how to distribute or how to use the proper operational modes. Second thing, obviously the performance of the drivetrain relies mainly on the control quality, in which control strategy plays a crucial role. The performance of the drivetrain mainly relies on the control quality. So control strategy is one thing and quality of control is another thing. Sometimes we decide control strategy but quality of the control is poor. Okay, we are not able to control the demanded power from by the driver. Okay, so with strategy there should be a control quality also. Okay, so the performance of drivetrain relies mainly on the control quality, in which the control strategy plays a crucial role. In practice, there are several control strategies that can be employed in a drivetrain for vehicles with different mission requirements. So what is meant by mission requirement? Whether the vehicle wants to drive through hill or desert, or it wants to drive through some sand or in the jungle, or it is going to drive through a city or a highway. So these are different mission requirements. So depending on that, the control strategies are to be developed. So we have to simulate different conditions in vehicle or HEV, and there are many drivetrain simulation available. With that, we have to check the control parameters. We have to check the different control strategies first, and then we have to implement them for different mission requirements. So there are mainly two types of controlling. One is maximum SOC of PPS, another is engine turn on and turn off or thermostat control strategies. So we end today's lecture here with introduction to the two control strategies, that is maximum SOC of PPS or max SOC of PPS, and second one is engine turn on and turn off or engine on off or thermostat control strategies. So in the next lecture, that is lecture 29, we are going to see maximum SOC and engine turn on and turn off of thermostat control strategies for series hybrid electric drivetrain. Thank you.